45 minutes to do all these next 3 steps. So hang on, hang in, stay alert. It's the last 45 minutes of the course with new stuff. So now we should open our minds towards the last input here. 2 proportions. Maybe, just maybe, when we do votes or surveys, we might be interested in what do female vote and what do males vote. What do white people vote, what do colored people vote, if it's in the US, or Latino people. I mean, there are different groups of people. Could we compare? Such comparisons are being made, I assure you. It could also be survival from cancer given a certain treatment. Either you get one treatment or you get another treatment. There are 2 proportions of survival in the 2 different treatments. You want to compare those proportions to prove one treatment better than another. Hey, it goes straightforwardly now with all the tools you have seen so far. There is a confidence interval for the difference between 2 proportions that looks exactly as you've seen confidence intervals previously. Then it goes like the difference between the proportions combined with the standard normal quantiles combined with the standard error of the difference of proportions, and the standard error of difference of proportions can be estimated like this. You can see there are 2 standard errors from one proportion, one from the other proportion. You add them up on the squared scale and you root them, and that's the result. It's the variance rules that I've shared with you. Now I don't prove it, but it's just the simple variance rules applied once again. Rule of thumb now is a bit more loose in the sense that now it's not 15, but it's 10 that makes this be okay. Rule of thumb. We can also do hypothesis testing in the same context. And there is a hypothesis test statistic which is very directly the generalization of the one that I shared with you 20 minutes ago for one proportion. Well, it's slightly different. Now I don't compare the observed numbers, I compare the proportions in this test statistic. In a way, I just divide by n, both in the numerator and the denominator. So it's the 2 proportions compared and the same standard error for the 2 proportions. Using a joint p in the... So I'm saying, hey, under the null hypothesis of those 2 being the same, if the 2 groups should have the same proportion, I compute the joint, the common proportion across the 2 groups by adding the number of successes and dividing by the sum of 2. Actually, if you like to make fun of Danish politicians, you can find, I have a link to a funny story of a Danish politician quite some years ago. I'm not going to mention the party now from which this person, I'm not going to mention the gender either, she is adding up percentages. she is adding up oh, what did I say there? she is adding up percentages in front of the parliament in the Danish Folketing. And she is not doing a good job in adding up percentages. She ends up, she's lucky that she doesn't end up with 250% or something like that, if her rule of adding up works out there. But anyway, it's a funny story, but we shouldn't make fun of politicians, so you can go look at it yourself. And we use the normal distribution. Now, it could be exemplified in this example here. This is a classical sort of 2-sample case where the proportion, so we would like to, in this case, there are a lot of words here, but let me just share with you that there were 57 patients using birth control pills, and there were 167 patients not using BC pill. We would like to compare for this particular type of illness that we're looking at here, the risk of this illness, whether or not you are using birth control pills, right? So there are 2 groups, those that use, those that don't use. We have a risk of getting this disease in each group. Did I bring those risks? Yeah, here they are. If you are in the birth control pill group, your risk of getting this particular illness would be 40%. It's a particular type of patients and a group, so it's not necessarily, it's not a general thing that would work. So don't worry out there. It's also a very old study, so it's a completely different. Now, I'm not talking about what is happening for you guys if you're there. And I guess if we divide people into those who use and those who don't use, you're all there, right? So don't worry, I'm not talking about you. I'm talking about this old study out there. If you don't use them for this particular case, what's the risk? 35 got sick out of the 167. So I have the two different risks. P1 had and P2 had, 40%, 20%. Are those statistically different? They appear to be, but I only have 57 in the one patient group and 167. Is this large enough to be significant? Well, if I were to use my formulas that I just showed you, I could first of all find the common P. Let me just look at that. What's the common P? That's the overall percentage, the overall risk in this patient group. I count all of them and all of them, right? I add all this bad events up, 58 bad events, 224 people altogether. So jointly there is a 26% risk. Note how this is kind of a weighted average of the two risks, right? Because there are more people in one group. So the 26% should be the joint risk if they were the same in the two groups, right? Now I could go on, and I'm not going to do that for various reasons. I'm not going to now try to exemplify this formula. I could use that formula for the difference between the two P's. I could use this formula for a test statistic, but I will jump to the next step instead. So we jump to the next video thing, because this more general thing that I will introduce to you now will include the situation, the two proportion situation that I already started, because I'm taking the step now that takes me to be able to deal with the Sundhedsstyrelsens 12 proportions case that I initiated today with.